So why don't we go ahead and get started? I'm quite a bit under the weather, so I'm not feeling great today. So I'm planning today to be a little bit shorter than other times, just because I don't know if my body can take it. But I didn't want to leave you all hanging since you guys have been so diligent about coming to class or coming to these meetings. And I enjoy talking to you guys so much. But just to remind you, last time we went through a little bit of a tour of particle physics. We reviewed concepts in the Standard Model. We talked about how most particles that are in nature are unstable. They decay rapidly. And we discussed the different decay mechanisms. So let me share my screen. I'll just go ahead and share this. You should see my iPad. Oops, sorry. So I introduced the particle data group listing of particles. We went to the website where this has been updated. And then I walked you through some of the lowest lying states that we see that are nuclear in nature, meaning that they're made up of quarks and gluons, which are the same building block of which we are made out of, right? Atomic nuclei are made out of just quarks and gluons and combine in different combinations. These same quarks and gluons combine into more exotic states. And we talked about the simplest of the configurations, which is the pion. And we talked about the different decay mechanisms. And here the color coding is tied to the force that is responsible for describing the source of the decay. So it could either be the weak nuclear force, electromagnetic forces, and then the strong interaction. Then we went down this list, finding that as you go higher and higher energy, it's much more increasingly probable that the dominant decay is going to be strong in nature. And also we started to see that the lifetimes got shorter and shorter and shorter. Okay. We talked about the things that are conserved in decay processes, paying close attention to energy and momentum in 2 as well as 3 particle decays. We talked about weak decays, where you can have a massive particle that it serves as an intermediate state, even though it's not a real particle. And then we consider the simpler scenario where we turn off weak and electromagnetic forces. And in that case, a few of the particles that are seen in the particle data group become stable, which weren't otherwise, while the vast majority still remain unstable. And so the strong interaction is so strong that for a lot of nuclear properties, it's fair to assume that the weak and the electromagnetic forces don't play a role, or they play a secondary role. And so you can treat them, you can turn them off at first, study physics in the absence of these, and then put it in, add them back after the fact using what are called perturbative techniques. And so these are the kinds of techniques that you can see in an intro course for quantum mechanics. We talked about why, as you go higher and higher energy, the different decay mechanisms for particles or different mechanisms for particles to decay start to grow. And this is because there's more allowed processes. And as a result, the lifetime of these particles can become increasingly shorter. And then we talked about how we can produce these resonances out in nature, or sorry, out in experiments. I consider the scenario in Jefferson Lab, in Compass, out at CERN in Switzerland, BESS-3 in China and Beijing. And here I consider the different scattering processes where you have some initial state. So time is always flowing from left to right. So here you have some initial state. These particles can exchange some other particle, in this case is a photon, and create the desired resonance that we considered, which is a rho. This can then decay to other particles. And so in different production mechanisms, so these are all different production mechanisms, you can create the same particle, namely the rho, or at least the different partners, not just the rho plus, but also the rho zero. And these are seen as dynamical enhancements, so rapid bumps, and so areas where the number of events grows, and the height of this, the location of the height and the width tells us information about the property of these states. And here I just made some final remarks about how these states are universal in nature. They appear in all allowed reactions. And so if we see one state in one reaction, namely if I see here the rho plus in this reaction, that's going to be exactly the same rho plus that is seen in a different reaction. Okay. My computer is a little bit slow. Let me see if I can close some stuff up. But okay, do people have any questions about this stuff? This is just a review of what we saw last time. What was the name of the rho particle? Does it have a name, or it's just called the rho? It's just called the rho. It's the rho particle is called the rho. So there's a lot of, let's go back to this list. A lot of the particles have Greek symbols. So pi, it's a symbol for the pion. And so the symbol on the top, the plus sign is just telling you is electromagnetic charge. And so the pi plus, the pi minus, that's what they're called. And then you can have a pi zero, right, which is the same particle, but it's in the same family as the pion. So the pi plus and the pi minus are actually antiparticles of each other. And so they have to have the same mass, exactly the same mass, and they have to have opposite charge. The pi zero, it's closely related to the pi plus and pi zero and pi minus, sorry. In fact, its relationship is very similar to that of between the proton and the neutron. So the proton and the neutron have a very, their masses are very close to each other. The proton is positively charged, the neutron is neutral, but their masses are very close to each other. In fact, if I turn off electricity and magnetism and I make the up quark and the down quark to have exactly the same mass, and the proton and the neutron have exactly the same mass, and so they fall under a family, and it's a doublet family because the proton and neutrons are two particles, so there's two in that family, while the pi plus, pi minus, and pi zero, they make up a triplet. So they fall under a family together. And other particles like the eta, right? That's a Greek symbol. The F0 500, historically that was called the sigma. That's another Greek symbol. The rho is just a rho. Sometimes you'll see that, so the number in the F0 500, the 500 is telling you approximately its mass. And so sometimes people will call the rho 770 because its mass is approximately 770. There's other particles that have the same properties as the rho, but they're higher in energy. So sometimes you'll see rho with a different number, and that refers to the mass of that other member of the rho family. So we have a question about what are the major differences between weak, strong, QED, and QCD? Good. Okay. So QCD is the strong. So it's the theory of the strong interaction. Okay. So QCD is short for quantum chromodynamics. And so this is the strong force. So it's the theory of the strong force. So this is the theory of quarks and gluons. Okay. Quantum electrodynamics is the subatomic theory of electricity and magnetism. So electric and magnetic fields are described at the subatomic level by quantum electrodynamics. And so this is the theory of particles with an electromagnetic charge and photons. So it tells you how photons interact with particles that are charged. Okay. The weak nuclear force, this is the theory. Essentially, you can just think of it as like the theory that is responsible for radioactive decay. So this is a little bit hand wavy, but it's a good, you can think of this. Okay. So it's the theory that describes how, for example, a neutron is not stable, and instead it decays by emitting a proton, a electron, and a neutrino. And that's what we talked about last time. Okay, so we have a question about what is the mathematical basis of Feynman diagrams? Or are they only useful for helping us visualize reactions? That's a great question. We're going to talk about that. So Rahul said, we did a bit of calculations to show that the total momentum is 0 under the center momentum frame. Does the method change if we consider the uncertainty principle? No. Yeah, that's a great question. Also, can we get all these particles using the scalar field theories? No, these are not all scalar fields. So a scalar field is the appropriate field to describe particles that have no spin. And so although pions don't have spin, in fact, the only one of these that has a spin is the rho. The quarks themselves have a spin. In fact, also do the photons, and also do gluons. And so we need something more complicated than simple scalar field theory to be able to describe the behavior of these particles. Okay. All right. So why don't we jump ahead? And so hopefully this serves as a nice little review for where we were going to go next. Okay. All right. So what I was going to talk about next is Feynman diagrams. Feynman diagrams are a useful tool to visualize equations. They also carry a physical interpretation to them. And so it's very simple for us to think about what kinds of mathematical objects can contribute to a given reaction. And so they both tell us about the physics that is happening, but they also tell us about the math that describes the reaction. And so what I was gonna do is essentially give you a little bit of a taste of these. And at first, it's very hard for me to be able to derive where they come from, unless you've taken, basically this is what we would do at the beginning of the first semester towards the second semester of quantum field theory, which in fact I'm teaching right now. So if you've taken an undergrad and grad quantum mechanics course, then you can start considering taking a quantum field theory course. Why is quantum field theory needed to describe subatomic particles? Well, there's basically everything becomes more natural in the subatomic world when you are thinking about theories that are, so quantum mechanics is the theory, or it's let's say the mathematical framework to describe particles that are subatomic, so very small things, and that are slowly moving. Okay. Well, Einstein's special theory relativity, special relativity, is a mathematical framework for fast-moving objects, or for objects moving at arbitrary speeds. Meaning they could be small, they could be moving slowly, or they could be moving rapidly. And so what happens is that for cases where you have particles coming at really high energies, so if you have particles coming in towards each other, let's say that this one has an energy of E over half, and it has a momentum that is in the negative direction, while this one has energy of E over 2 with some momentum in the positive direction. And so here I'm considering the center of mass frame. So if, and let's say these particles, I'm just going to think about some simple case where my particles have mass equals to m. Okay, so all my particles have mass equals to m. Okay, so if I move some of the stuff over here. So if E is greater than 2m, right? So I need the energy of the system to be higher than the mass of the two particles because they're moving in general with some non-zero momentum, right? But it's less than, let's say, 3m, then the only thing that can happen is that after my reaction, I will have two particles going in equal and opposite direction. And they would be the same particles with the same momentum, okay? So let's make them black lines so that we don't get confused. Okay. But if E is greater than 3m, well, we know that energy, so we know that mass is a form of energy. And so this energy can be transferred into the production of a new particle. And so you can have now reactions where you have multiple particles being produced in your final state. In this case, they all have the same mass. Okay, so that's perfectly allowed in nature. And this is, of course, a consequence of us considering reactions as sufficiently high energies. And in experiments and in nature in general, we do have conditions to have such high energy so you can have these types of reactions where you can have particles being produced in the final states. This is something that quantum mechanics fails to describe. Quantum mechanics just cannot describe that. So you can, but it's a little awkward, basically. It just becomes unnatural. And so the most natural framework is to promote particles to be excitations. That's not what I wanted to do, but it's okay. Let me just delete all this stuff. So the most natural thing is to consider particles to be excitations of some field, which given some energy, the field would perhaps look something like this. And it's just associated with, you've created some particle with some energy of m, let's say. And so in quantum mechanics, you say that particles are both waves and particles, and the object that you use to describe the interactions between particles and the properties of particles are wave functions, which satisfy the Schrodinger equation. In quantum field theory, what you describe instead are fields. So what we consider are fields that the excitations of these fields are particles, and what we end up evaluating are interference between these different fields to give us information about the properties of the particles as well as how they interact. Okay, so this is a basis. This is a basic concept of quantum field theory. Of course, not gonna give you any further background on that. It's just a little bit of a taste. But what we can do is that within this framework of quantum field theory, you can then show that almost basically every physical observable can be written in terms of Feynman diagrams. And so today we're gonna introduce the concept of Feynman diagrams for a simple field theory. I'm just gonna give you the rules, and I can't tell you where they come from because it's outside of the scope of this little review, but at least you get to learn the basic ideas, and then you can evaluate Feynman diagrams on your own. Okay, at least for the simple theory. Okay, Are there any questions at this point?
So why exactly is quantum mechanics not helpful in the previous example?
Yeah, so what ends up happening is that the quantum mechanic, so in the Schrodinger equation, what you're describing, so in quantum mechanics, what you're describing is a wave function of a single particle. And the problem is that as you go to higher and higher energies, the wave function can basically you can have transitions between one particle and many particles. So basically what you evaluate are, so when you have for example, if you have a single field here, the field could have couplings to other excitations. So you can have multiple excitations happening inside of the field. And so the field is a natural way for us to be able to describe multi-particle physics and the transitions between two particles to many. While in quantum mechanics, the thing that you're always describing is the wave function of a single particle. And that just turns out to be, although it's fine for low energies, it's pretty rigid when you're considering higher energies. And then you can have transitions between basically when you can start producing particles. And so also it's naturally the Schrodinger equation. So the Schrodinger equation looks something like this. You have I d ht psi is equal to so if I remove h bars from the expression, what you end up having is essentially this looks like this is essentially the Hamiltonian. So let me just write it as a much more simple expression. So I have that the Hamiltonian, which is some operator that acts on the wave function. This is my wave function. Is equal to the kinematic term plus the potential. And these are operators that are acting on some mathematical object. These are wave functions. And here you have this is a potential. And so the basics of quantum mechanics, namely the Schrodinger equation, tells me that energy is equal to kinetic energy plus potential energy. Is the basics of it. Okay, there's some complicated. There's some complications, obviously, because these are not scalars. These are operators, meaning this acts like a matrix and this acts like a vector in some space. But this is the idea, right? And this is purely non-relativistic. Okay, and so you're already stuck with that, right? So you have a non-relativistic theory. You can say, well, what if I start promoting this to a relativistic, can I write down relativistic quantum mechanics? And you can. So you can. It's just it starts to become hairy. So, and that would be what you would need to then describe particles that are going at higher energies, right? Non-relativistic physics is basically the physics of objects that are moving slowly. If you want to then start describing higher and higher energies, you can certainly try to do that with relativistic quantum mechanics. But you end up getting challenges as soon as you start producing new particles, and so it just becomes a non-elegant way of getting about it. And so there's also more technical aspects, which is the Hamiltonian. There's some underlying symmetries in nature that seem to be fundamental in nature, and these are not described well or they're less evident when you think about the Hamiltonian. These become a lot more clear when you think about, instead of the Hamiltonian, you think about what are called Lagrangians, and field theory is much more, makes this emergence of these symmetries much more apparent. And so, okay, that's my hand wavy response. Hopefully it didn't confuse you more than it had to.
I learned that in QFT, for getting a single particle, you just operate a dagger with the vacuum, right? Can you show me how to get to two particles, and if the mass of the two particles can be equal to mass of a single particle?
Okay, so I think you're a little more advanced than other people, Jumana. So I don't want to go down into technicalities, but I can show you at least the first part of your question, which is straightforward. You're saying I can create a particle with some momentum out of the vacuum using the A dagger operator. That's absolutely true, right? This is a vacuum, which is the state that has no particles present in it. And I can create particles by using creation operators. So it's a creation operator. Creation operator, right? For a single particle. There's some details here that I'm going to gloss over because of what I just said. This is outside of the scope of this meeting. And what you can do if you want to create two particles, the simplest thing you can do is just have two creation operators acting on the vacuum. One with momentum K, the other one with momentum P. And they would, in this case, it would have the same mass. Does this answer the first half of your question?
Yes, sir.
Okay, sounds good. Okay, so Adriana had a question about when I say that the particle is an excitation of a specific field, is that an energy field, a mass field, a scalar, etc.? I might be completely misunderstanding. No, those are good questions. So the way that you can define particles that are you can define fields that are in energy space or momentum, for momentum space. So let's say what I mean by for momentum is Einstein's for momentum, where you have energy is one, you can treat a momentum as a four-dimensional object with the zero component being the energy, and then the other ones being the momentum along the x, y, and z direction. Okay, so you can define fields in this space, no problem with that. You can also define fields in position space, meaning here position would be a four-dimensional object, so you can create a field at some time t that is located at x, y, and z. You can do either one of these. And so you can do, this is the most natural basis, momentum and position. You can construct more complicated ones, but these are the most natural ones that you see in the beginning of a field theory course. Whether the particles, so remember, mass is only an example of energy. And so if you have a field that is in energy, meaning you create some field with some form, you use a field to create some particles because there are excitations in this field with some definite form momentum, then that would have, the particle will have some energy and momentum, right? Or alternatively, you could put it in some position in time and as well as space. You can't fix both the position and momentum because of the uncertainty principle. So you can choose one or the other, or some complicated linear combination of these, okay? Whether the fields are scalars or otherwise depends on the spin of the particle. And so this is an intrinsic property that all particles carry. And this is, if the particles are static, it looks like they carry a spin, meaning it looks like they're spinning around some axis. And so particles carry this intrinsic property that kind of looks like a basically they look like a little ball that is spinning around some axis. They're not really spinning about their axis, but it looks like that. And so particles that have no spin, so if they have no spin, so it's just like a little blob with no spin, this would be a scalar. And then if you have a spin that looks like a vector, then the field would be a vector. If you have a fermion that has a spin 1/2, you need a special kind of field for that. So for example, the photon looks like a vector, the rho looks like a vector, gluons look like vectors. And so for that you would need a field that it looks like a vector. Okay. For things like the Higgs, which is a scalar, or pions, which are scalars, you can just use a scalar field. For fermions, like electrons, you would need another type of field. This was introduced by Dirac, and so typically these are called Dirac fields, and they're spin 1/2 fields. So things start to get more complicated, but basically it's well understood how to treat these particles given some fields. Does the wave particle duality play into the QFT description of particles? Yeah, basically everything that you know and love about quantum mechanics can be described in terms of quantum field theory. Quantum field theory is just a more complete description of quantum mechanics. Quantum mechanics is incomplete because it doesn't describe high energy reactions where particles are relativistic and you can create other particles. But quantum field theory does. And so everything that you know and love about quantum mechanics, it can be encompassed in terms of quantum field theory. It has to. And so, all right.
So one more question.
Sure.
Like we have the 4-vector momentum, right? So we have 4 components. So if we take a vector field, then if the spin means we have only minus and plus spins.
Sorry, I can't hear half of your question. So we have 4 momentum.
So I'm saying that the spins are usually minus and plus, right?
If
So
you have if you have a spin 1/2 particle, yes.
What about spin 1 or spin 2?
Then you have 3 helicity components, unless so basically you have 3 components.
So it will be a vector with 3 components?
Yeah. Yeah, it would have 3 components of the spin. Okay. So if a point in the field has an energy E, does that mean that there will be a specific particle there, which that amount of particle can give rise to? No, you can have, if you have you can have, basically a field could create multiple particles. So depending on the energy and depending on the quantum numbers. So it's a little more complicated than that. You have to specify not just the energy, but you have to specify also the momentum. So, but okay. But I think maybe we can table these questions. I'm glad to hear that people are really excited about quantum field theory. It is a really beautiful concept, but it's something that you wouldn't see until grad school. But there's some books out there that can serve as a nice little introduction. One thing that perhaps would be one book that I really love, that is a good reference for at least for you to get familiarized with the introduction to particle physics, and you get to learn about all the history and you can learn about some of the basics of Feynman diagrams and different properties of particles, is this one. It's Griffith's Introduction to Elementary Particles. That's a very, very nice one. So if this is something that interests you, which it seems like it does interest most of you, I strongly would recommend you guys getting this. And the first chapter is actually a very nice introduction into the history of it, into the history of particle physics. So the first one is called Historical Introduction to Elementary Particles. And then after that, in chapter 2, you start seeing elementary particle dynamics. And so you learn a little bit about the forces, as well as quantum electrodynamics, quantum chromodynamics, weak interaction, et cetera, et cetera. So a lot of the things that we're touching on. And this is pretty good for an undergrad. And so if you're an undergraduate or you're really excited about this stuff and you're in high school, you want to learn about it, I would encourage you to think about getting this book. Okay. So, okay, so I'm seeing a couple more questions. So can we separate fields? For example, electric and magnetic fields should be interwoven with the photon fields. Yeah, so what actually gets this is described in electricity and magnetism is it's not the electric and magnetic field, but you have a field for, this is a symbol for the photon field, which is typically called a mu, telling you that it's a vector. It has a Lorentz component into it. And you can, what this is describing is the electromagnetic potentials. So, from which you can get the electromagnetic fields by just applying Maxwell's equations. And so you can construct the electromagnetic fields from the potentials, which is the fundamental object that appears in electricity and magnetism. Okay. And then you can have the field for the electron. And you can start describing interactions between electrons and photons using Feynman diagrams, as we will touch on in a second. And so they mix with each other, they interact with each other. Okay, so so we have a question about a nice question, which is, what is a field? That's a very good question. So think about a mattress or a sheet. So a field, so let's say that you're, let's say that I wanted to describe the height of your mattress, okay, for every single point in space, right? And so let's say your mattress goes from x equals 0 to your length of your mattress, which is x equals L, okay? And of course, your mattress is not perfect, right? It's not like a perfectly flat thing, right? It's a little bumpy, and then it has like some points where it goes down. And so it looks something like this, right? And so if I want to describe the height of the mattress, I can use a scalar field, which is just for a location. I can say this is some arbitrary location x. this is my value of the height at x, then the field is nothing more than the function that gives me back the value of my height at that position. That's one simple scalar field, something that you give it a number, right? And this could be two-dimensional. So, right, it doesn't have to be, because your mattress has not just a length, but it also has a width, right? And so this thing, you know, looks kind of like a rectangle, right? And so I can, you know, make it something like this, right? And so the field could depend not just on x, but it can also depend on y. But the point is that it's a scalar field because you can give it as many variables as you want. And this could also be a function of time, right? Because, like, you know, if nobody's sitting on your mattress, at some point it's going to have some shape, right? But if I then sit on it, then there's going to be some, you know, I put my body on it, and then some ports are going to dip down, right? Like some points are going to be more shallow, right? So the height can also vary with time. And so the mathematical functions that describe the, you know, the height as a function of the location in both in the length and the width and time, I can use to describe, I can describe it as a field. Okay, so it's a scalar field. All right. Another example, I see somebody was saying temperature is a good example. That's a great example. So another example is a vector field. So this is, so imagine now that I wanted to measure wind. I want to determine the velocity of wind at any point, right? Well, here, let me call that v, which is going to be some vector. It's going to depend on time, on x and y. And so at some point, the wind is going to be moving in some direction with some velocity, with some magnitude, right? It's going to be, and another one's going to be different. And now here I'm going to make it a function of not just x and y, but also z, right? Because the wind is different depending on the height. And so you will have and so at any point, right, the wind has some magnitude and some direction. And so that means that at this one point, I'll have an x component to it. I'll have a y component, because it's pointing in some direction, as well as some z component. And so it's a three-dimensional vector, right? Because it's telling me, yeah, it's describing the behavior of the wind in three directions. So this is an example of a vector field. So this is an example of a scalar field. There's many examples. This is one of them. This is an example of a vector field. Does that help, Abby? Or wait, oh no. Who asked that question? It wasn't Abby. Okay. Great. Okay. So, all right. So this has been a nice little detour, but let's get back to what I was trying to do. Which is, I'm going to introduce the simplest theory, which is, for those of you that are experts, it seems like there's some of you that are know quite a bit about field theory. This is an example of a theory that is a scalar field, and it's typically called a lambda phi 4 theory. And the reason why is because it's a scalar field, and you can have interactions where four particles come in at the same point. Okay. And so the only possible way that particles can interact is this way. It's in this example, this vertex right here. And so what can happen in this theory? Well, I can have particles that, if I shoot a particle, it can just continue going and going and going. So if I shoot it in at some point, and it's carrying some momentum p mu, which is my symbol for energy and momentum along the x, the y, and the z. At some later time, initial time, later time, then it can keep on going. Nothing else. So if I have a single particle, nothing will happen to that particle. It will just continue propagating forever. Okay. So it's propagating, just traveling forward in time. Okay. And we'll touch on in a second what the object is that describes this propagation. Okay. This is great, but it's a little boring. It's not telling me much. When life starts to get more interesting is when I have two particles coming together. So there's no arrows. I'll stop. So the time I'm going to draw going towards, time is going towards the right. And I'm not going to put any arrows on the lines, okay? So if I have two particles, so let's say here's one particle, it can just propagate, nothing else. Two particles. Life starts to get more interesting. Okay, so what could happen if I just shoot two particles, and let's give one some momentum p and the other one some momentum k. Well, at some later time, there's some probability that they just don't interact with each other, right? There's just some probability that they're just going to keep on passing through each other and nothing happens. Right? Particles are passing through each other all the time. In fact, we have neutrinos shooting through us all the time. And most of the times nothing happens. And so this can happen. No interactions. Which equals boring. Right? We want to see things. We want to see something happening, right? Okay, so this can happen. What else can happen? Well, what can also happen, and I'll add it to it. This isn't, this is like an arrow saying what are the things that can happen. It's a symbol that I'm making up. Well, what can happen? The particles can interact, right? And I'm allowing for that interaction to happen. So I'm letting particles propagate and then interact. And so they can interact. Woohoo! Look at them interacting. Okay. But this is not the only way they can interact, right? If they can interact once, quantum mechanics says that everything that is allowed can happen. Anything that is allowed can happen, right? So maybe before I ask the question, what else could happen? But maybe somebody can tell me what happens to the energy and momentum across this vertex. What has to happen to the energy and momentum across this vertex?
Momentum is conserved
Momentum is conserved. Very good. So the
and energy could change into mass.
the energy could change to mass, right? But the energy, the total energy, is it conserved or can it change?
It is conserved, but some of it could be mass, conserved in the form of mass.
Very good, very good. So that means that, in fact, what I'm going to do is that I'm going to change my notation a little bit to make it super, super obvious, okay? So I'm going to say that some particle is carrying momentum k, all right? And I'm going to make this one not carry p, but in fact, I'm going to make it that it's carrying p minus k. Okay. And so this is p minus k over here. This is k, okay? And so the total momentum has to be conserved, right? But the total form momentum. But I can make this q, right? There's nothing that's stopping me from giving this particle some momentum q. Okay, so what does this have to be? This, what momentum does this have? The form momentum does this have to have?
P minus Q.
Very good, awesome, great. So you see that at the beginning of the reaction, because time is going forward, right? Time is always going forward. So at the reaction, total momentum was P plus P minus K plus K, which is equal to P, right? And so at the end, right, the total is equal to P minus Q plus Q, which is equal to P. I haven't broken anything. Very good. That's great. Okay, so this is my symbol for particles to interact once. Okay. Can they interact more than once? I see Aditya nodding his head. How many? Okay, so if they can interact more than once, what should I draw? That wasn't a rhetorical question. I'm waiting for guidance. Somebody tell me what to do.
Maybe a second similar reaction.
All right, so I have some reaction where I have this, and you're telling me I should draw another one like this?
To the right, yeah. So that just sort of show that it follows.
Okay. What should I do? What happens in between? Do the particles just disappear?
They propagate.
They propagate. Okay, so that means that this propagates, and so what should I do? Should I connect this line to this line? Very good. Okay, so let's redraw this. And so they can propagate. Okay, so the particles can interact once, they can interact twice. Is there any other ways that they can interact twice? Can anybody think about other ways that they can interact twice?
Perhaps if another particle is created in the first reaction, then all three could interact.
Perhaps if you mean if I create a.
I don't know if that would be an equivalent case or.
Well, this is the only vertex that I have available, right? And I have two particles in the initial state, right? And so this doesn't seem to allow for me to have one particle in the final state. So I see Aditya.
So, So we have that vector. So we are saying that how we can do it twice, right? So we can have one of the particles decaying that were created from the ones that were created.
Well, we can't have decays that are not represented by this rule. So the only way that they can interact is this rule right here. So if you can explain to me how I can have a decay with this one possible interaction, which is literally saying you have particles coming in, they interact, and then they go away. I can, in principle, have a part, I can think about this as like a particle coming in this way that then decays to 3. That certainly can happen. But
yeah, that's what I meant. That the particle goes out and it decays into 3 of the particles.
The problem, though, is that I have 2 particles coming in, right? And so you're telling me I have this, right? And then how do I connect them again?
You can connect one of the decayed particles to the first one.
I can have this, is what you're saying. And then I have this.
Yeah, is that possible? I don't know.
Yeah, this could happen. This is, if these particles are going to be real, right? I have to go to much higher energies, right? Which is fine. Yeah, okay. So this would be an example where we are producing, so we're producing 2 particles, 2 particle production. All right, I'm gonna put that one aside. The one that I was trying to get you guys to think about is simpler than this one, which is you have 2 particles, right? And I think Aditya had interesting idea about exchanging photons. The problem is that we don't have photons here. There's only this one field. But what you can exchange are 2 particles. And so you can have this happening, where the 2 particles come in, they exchange 2 particles, and then they go off on the merry way. And in fact, there's yet another way you can do this, but this is a little more complicated to explain, which is you exchange not just particles, but you exchange the final particles. This is more complicated. So this one we can forget about this one for now. Let's forget about this. But basically what's happening is that if the particles are identical, you don't know where the particles are going. They're what are called indistinguishable. So you can't tell if you detected this particle or you detected this particle in your detector. This is my little cartoon of a detector. I see them here. It's a little bucket. Okay, so that's all nice and good. So these are examples of ways that particles can interact. They can, of course, interact any number of ways given this one rule. So let me draw another example. Examples like this. You can have many of these, right? These little bubble diagrams. So this can happen any number of times. And so you can have reactions like that. You can also have more complicated things like you can have things like you can create you're creating here a particle antiparticle pair, and then they annihilate each other. So create a particle and its antiparticle, and they destroy each other for a short instance of time. So that can happen. Esha had a question. Esha, what's your question?
What does it mean to represent something on the vertical axis here?
The vertical axis. You mean like this right here versus this right here?
Yes.
Yeah. So the point is that time is going forward. It's going this way. So I'm always assuming that time is going this way. And so here's what's happening physically. In the first reaction, you have two particles coming in, right? Time is going this way. The particles interact, right? Then they travel, right? They both travel. And then some later time, they interact one more time. And then they travel. And then you smash them originally with each other, right? And then you say, I saw a particle over here and I saw a particle over here, okay? So here time, the separation between these things this is happening at some time, let's say t equals t1. I got, this could be, let's say, let's just call it t1. And this happened at some later time, t equals t2, which is greater than t1. Okay, so that's what's happening there. The difference of the other one is that the other one I can draw a little bit different. So what do I have? I have, so this is this diagram, right? It looks like things are traveling at the same time, right? It looks like the time of this event and this event is exactly the same. That could happen. Well, I'll put a caveat to it. But what more physically you can imagine is that you have a particle that then decays to three particles. I think this was the question that Jumana was trying perhaps to allude to, or the example she was trying to allude to. So you have two particles that are, so one decays to three particles, okay? And then the other one is just coming along. And then at some later time, these particles get absorbed into this one. And then this one keeps on traveling. And so here at t equals t1, your particle emits particles, right? And then at t equals t2, your other particle absorbs particles. They get absorbed and then they become one.
Okay, got it. Thank you.
Is this the example you were thinking about, Jumana? Sorry, perhaps I confused.
Yeah, I was actually thinking something like that, but I deviated from it a bit.
Okay, cool. All right, sorry about that. So Leo has a question. Why can energy change to mass but not mass into energy? No, they can. Mass is just an example of energy. So you can have mass that gets transferred into energy and vice versa. If the mass changes, does the momentum change? No, the momentum always is conserved. So you can have, the energy is always conserved. It just so happens that mass is an example of energy, right? This is the most famous equation, right? E equals mc squared. What this is telling us is that at rest, this happens when the particle is not moving, so momentum is zero. At rest, the mass of a particle is equal to its rest energy. And so you can transfer mass into energy or energy into mass, either way, okay? And everything that I'm considering, I'm setting the speed of light equals to 1, okay?
Sir, I had one more question.
Sure.
Sir, so if the two particles that are created are going in the opposite direction due to the conservation of momentum, how do they come and meet? Means you would have to exert some kind of force.
Jumana, so sorry, I can't really hear you because there's a lot of noise. Could you maybe write your question on the chat? It's just very hard to hear from the background noise. In the meantime, while you write that, Aditya, what's your question?
I think she was trying to get at the same thing, that might just be a sort of geometric representation, but if the particles come together, interact, and sort of go their separate ways, how do we consider that they would come in this like curved trajectory and come back and collide? Like, wouldn't they be diverging from that place? And then how would we consider them to come back together?
So it depends. This depends into, so let's think about energy. The total energy of the system. E. Okay. And here I'm going to set the minimum energy that two particles can have. Okay. And so the question is, what happens when I smash two particles against each other, right? Well, below this energy, I don't have enough energy to create my two particles. So that's not a good question. I need to be above this energy to be able to ask this question, okay? And now let me put here enough energy to create three particles. In fact, let me move this down a little bit because I'm going to run out of space. And let me put here enough energy to create four particles, okay? So if I shoot two particles against each other, let me make this like a black box. This is, in fact, all the ways that particles can interact, okay? This is my scattering amplitude. This is the object that we've been studying, okay? Then if I think about time going this way, then what can come out? How many lines can come out?
Only two.
Only two, right? Nothing else can come out, okay? And so quantum mechanics and quantum field theory tells me that anything that can happen in between that is allowed by the theory will happen. And so I will have these exotic, I'll have things like just a particle scattering, two particles scattering simply, or recombining, scattering multiple times, or exchanging these, these exotic intermediate production of particles so they can get reabsorbed. Anything is allowed to happen that is allowed within the theory, okay? And so this is a huge black box for all the intermediate stuff that can happen in between, okay? Now let's go to higher energies. Okay, I think that partly answers your question, right? It's like, why do these weird recombinations, these productions of particles and recombinations can happen? And the answer is because it's allowed by the theory. There's nothing that tells me that they can't happen. As long as what needs to happen is that as I go through each vertex, right? This has a momentum P minus K, this is a momentum K, this is a momentum Q, this is a momentum P minus Q, right? And so what is the momentum that it has to be flowing through this here? Well, it's got to be, so there's going to be two momenta, right? One for this guy and one for this guy, right? And so if I say that Q is going this way, right? Q is going this way. K is going this way, right? And so the sum of this guy and this guy has to be P minus Q. I don't know, or K minus Q. I don't know what it is, but the sum of them, or I don't know the individual ones, but I know that the sum of them has to be K minus Q. So it has to be this, and I'm going to call this one L, and this is going to be L. I don't know what L is. I don't know what it is, but I know that the sum of these guys has to be K minus P, or K minus Q, sorry. So if it's allowed, if it basically any vertex that conserves momentum and energy is permitted, and you can create any intermediate particles as long as they're not, you don't have intermediately, you won't see them as long as you don't have enough energy to create them. Okay. All right. So what happened? Okay, go ahead.
Yeah, I'm so sorry to interrupt. Actually, the thing I kind of meant was that once they interact and they sort of seem to go in their separate ways, right? Like they would have a physical momentum which has a direction. So how does that propagation, which might be in a different direction, lead them to come together again and sort of form this like curved trajectory and come back together?
Yeah, that's a good question. So you're thinking about it physically, right? Like physically in classical, if I think about classical particles.
Yeah, exactly.
Yeah, so most of the reactions that happen in quantum mechanics are not allowed classically. Yeah, that's a great question. So the quantum mechanics world is weirder than the classical world. So it's not that you can literally have particles that can have any momentum and then recombine. These are allowed if they're not physical particles, if they're not acting like classical particles. Does that answer your question? All right. The answer is typically quantum mechanics is weird. Okay. So, okay, so if I go to, let me just finish this exercise. If I go to energies above 3M, then what could happen?
You have more than 2 particles coming out.
Yeah, so let's say that I shoot 2 particles coming in. How many particles can come out?
3 particles. No?
Well, let me ask first. Can I have 2 particles coming out? Is that allowed? Yes. Okay, good. So this is an easy question. This is the easier part. The harder question is, given my theory, can I have this? This is a question. This is what you were suggesting, Adriana, right? Yeah. This is a harder question, right? So the question is, can you draw, just given your 2 rules, right? That lines can propagate and you have vertices like this, right? Can you draw a diagram like this? Can you draw any diagram that will result in having 2 incoming particles leading to 3 particles going up? So maybe to Adriana, how many are the number of legs in this vertex? Are they even or odd?
There would be 5 total coming out, so odd.
So this one would be odd, right? But my building block, which is this one, is it even or odd?
Oh, it's even.
Right. So can I construct diagrams with an odd number of legs from vertices that only have even number of them? I see you shaking your head.
I guess not then.
Sounds good. I think I agree with you. So this is not allowed. So here's an interesting thing. So here's a great example of something that just by energy, it would be allowed. There's nothing that tells us that, unless I know the theory that is describing this, that this process wouldn't be allowed, right? This is, so in the technical jargon, this is something that is kinematically allowed, right? But it's the dynamics, it's the theory, right? This dynamical theory that is telling me how particles interact, that then tells me that this is just not allowed. All right.
And that comes from the definition, right? Like the definition of what we defined as an interaction, that like open white circle.
Yes, exactly. Because every interaction that I construct, it's just going to be some linear combination of these guys and this guys. Cool. All right. So last but not least, above 4 particles, right? I can certainly have 2 particles going to 2 particles, right? Can I have 2 particles now going to 4 particles? Yes.
Yes.
Adriana. Yes, very good. This is the example that we considered. In fact, here, this is the one that Jumana made us consider, which is this example. Perfectly allowed, right? All right, cool. All right, so hopefully this gives you a little bit of intuition on how you can, given some building block, construct different contributions to scattering amplitudes from Feynman diagrams. But what do they mean mathematically, right? Like I haven't told you what they mean mathematically, okay? And so in this theory, in this very, very simple theory, this vertex gets a very, very simple definition. It's just a parameter. And it comes in with a factor of I minus I. The minus sign is convention, okay? Just convention. This I is important, right? This I is nothing more than the square root of -1, okay? But this is important. And this is just a coupling, just some parameter. Which in principle, I don't know, but I can tune it to match to experiments, okay? So that's the only thing. So here's my Feynman rules. There you go. You're learning Feynman rules. Okay. All right. So rule number 1, vertices. Okay, just that one. You get a minus I times lambda for each vertex. Okay. Rule number 2. If the for external legs, meaning these legs that stick out, okay, for these little legs that stick out, okay, you get just a factor of +1. Super easy. This is because they're scalars. So if they have a spin, then this is more complicated, okay? But for scalars, you just get a factor of 1. All right. For internal lines, these are called propagators because they're telling you that particles are propagating. Okay, if this has some momentum, some forward momentum p, okay, this gets this is equal to I over p squared minus m squared plus I epsilon. I'll come back to this epsilon, okay?
So, sorry to interrupt. What are these rules exactly? Are we trying to build an equation for our diagrams?
Sorry, can you repeat the question again?
What are we trying to do? Are we trying to build an equation for our diagrams or?
Yeah, I'm gonna give you some examples of Feynman diagrams. And I'm gonna ask you to write down those equations. And just so you can at least start figuring out, get some intuition of where these equations come from. I'm not gonna make you evaluate those equations because they're gonna be, in general, some complicated integrals that you have to evaluate. So at least you can write them down yourselves. With enough training, you will be able to evaluate some of them. That's what I was thinking about.
And so the lambda, is it just the number which is getting multiplied with the, I can say the A daggers? I don't know how to do the coupling. So.
Yeah, the lambda is just some parameter. It's just a number. It's a real number. Just a number. I'll give you some examples. Don't worry, we'll get there. I'm just giving you rules, right? I can't tell you where they come from. They come from, I mean, they basically come from constructing the theory in quantum field theory, and then you can treat free particles exactly, and you end up getting propagators for them, and interactions, you can treat them perturbatively. And that's essentially where this comes from. but intuitively is what we were just talking about. Feynman had originally designed these diagrams for QED and electromagnetic force. Yeah. So originally he was interested in QED, but this Feynman rules hold for, you can construct Feynman rules for any theory. Sounds good. Any other questions?
So how long, means how much is left to discuss actually? I have to be somewhere else.
I don't know, 10, 15 more minutes. Is that okay?
The recordings will be available, right?
Yeah. Yep.
Okay, thank you.
Okay. So m is the mass of the particle. And then this thing, p squared, is equal to the energy of the particle minus the momentum squared, which is minus px minus py minus pz. Okay. Epsilon is an intermediate parameter, and ultimately we're going to want to set this to 0. So ultimately we're going to set this to 0. So this is a technical issue that is very, very important. So I flag it here for some of you, but you can ignore it for if you're just beginning to see Feynman rules for the first time. Okay. And then the last thing, well, there's 2 more things. 4 is if you have intermediate undetermined momentum, then you need to integrate over it. So so this means that you'll be integrating over it, and you'll be integrating over it something like this for each intermediate momentum. So this could be, let's say, K1, T4, K2. There's these pesky factors of 2 pi to the 4th that are important. And then in general, you can have any number of any intermediate momentum to integrate. Okay. I'm almost done. I have one more. Does anybody know what's the last Feynman rule that is relevant for this? What kind of particles am I thinking about? They're scalars, right? So they're identical. Are they fermions or bosons?
Fermions.
No, they're actually bosons. So they're identical. They have no spin. So what needs to happen is that there's symmetry factors associated with the fact that you can't distinguish between the intermediate particles. So you have to, there's yet another technical point, is that you have to divide by a symmetry factor. This is equal to the number of permutations of internal lines that leave the diagram unchanged. So I'll give you an example of that, but that's it. So only 5 rules, and this 5 rules, I know they might seem daunting at first, but like, think about it. If I have these 5 rules, I can draw any diagram and in principle translate that diagram into a mathematical object. So that's quite powerful, and that's why Feynman rules are so powerful. And this is why, I mean, that is partly why Feynman was so fast in doing his calculations. And so this is a remarkably powerful tool. It doesn't give you what the diagram is, right? You have to write it down, and then you have to evaluate some integrals, but it allows you to get some diagrams relatively fast compared to others. Probit is asking if the epsilon in the previous case in the propagator is there to deal with possible singularities. Absolutely, that's exactly what you're doing. So there's this propagator. Notice it has a pole. It has a pole when p squared is equal to here, actually, this is a great question. I know that some of you have to go, but this is what happened. There we go. So it has a pole when p squared is equal to m squared, right? And so p squared, remember, is equal to the energy squared minus the spatial momentum squared, right? And so then this tells me that E squared is equal to P squared spatial momentum plus M squared minus I epsilon, right? And this is actually the general form of Einstein's theory of relativity, right? At least the relationship between energy and moment and mass, right? And this tells me that I have two solutions. I have I have to take the square root, right? But I can have positive and negative solutions. The positive solutions are associated with particles. And so what this does is I can look at the energy plane. And so I'll have a particle that is has an energy that is, if this is equal to, I mean, I can Taylor expand this and say this is equal to P squared plus M squared, square root it plus or minus. I pull that out. Yep. 1/2. Trying to do this exactly, but it's E over square root of E. Here, sorry. So what am I doing? I'm pulling out this, and then I have 1 minus I epsilon. Square root it. That's what I was missing. Very good. Oh no, there's no. Sorry guys, I'm getting distracted. There we go. So I can pull this out. So all I did was just pull out this guy, and so I'm left with an epsilon. Then I can assume epsilon is small. Taylor expand this. I'll get a factor of 1/2 on the denominator, and then I'll have a factor of 2, and then I'll have this, and then P squared, something like this. And so this is shifting the position off into the complex plane just a little bit by some amount epsilon prime, let's say, okay? And then the other position, this is when E is equal to 0, and then here I'm shifting the energy by a little bit. Okay, I know it's a little fast what I just did, but basically what this is doing, the epsilon is letting you go around this axis and be able to do integrals, and you're shifting the epsilon. It's telling you how to deal with this epsilons. So what I did is that I defined this to be equal to the square root of epsilon times this. And so I'm saying, because epsilon is going to 0, then it doesn't matter what this is. This whole thing is going to 0. And so I'm calling that epsilon prime. Oh, I see what you're saying. Oh my God. Yeah, you're right. Yeah, this is what happens when you do fast and dirty calculus. Okay, so this should be delete. This should be in the denominator. Very good. All right. So that should be right now. Okay. So this whole thing right here, I'm calling this whole thing right here, I'm calling epsilon prime. Okay, so that's what the epsilon is doing. And so when you have to evaluate an integral, then this thing gets shifted by a little bit. Okay. All right. Now, before I wrap things up, let me just give you some example of Feynman diagrams, and then I'll leave you guys with some examples, and then you'll have to do this at home. Does that sound good? All you have to do is just write them down, just getting familiar with them. Okay. So here's my first example. Well, contributions to the scattering amplitude, which is equal to, which we call which we call M, which is this thing, right? And so the first one that I can write, right, is just this guy. That's the first contribution. So the scattering amplitude is all the diagrams that connect two particles to two particles, and they're connected. So there has to be some connections. So for example, this equals all connected diagrams. Because the particles have to interact. So for example, this it's not inside it's not inside M because it's not connected. Okay, this is an example of a diagram that is disconnected. And it makes sense. The particles just travel, they never interact with each other. So it's not going to tell me anything about how the particles scatter off each other. And the particles have to scatter off each other for us to count it as a contribution to a scattering amplitude. All right, I'm seeing some head shaking, so hopefully that's good. All right, so, okay, this first example, what should this be, this one? The first example, what should be this contribution to a scattering amplitude given the rules that I wrote down in the previous slide?
Would it be minus I lambda?
Very good, minus I lambda. Easy. Okay. All right, let's think about the second example that we drew down. This one already starts to get trickier. So I'm going to do this example. Yeah, Harshit.
We have to add one for each external leg.
Yeah, it's multiplied. So you would have 1
Okay.
times 1. Very good question. So you just get a factor of 1 for each leg, and everything is multiplied. Sorry. So in the Feynman rules, everything is multiplied. Okay. So for each contribution, everything is multiplied, and then you add up the contributions together. Okay. All right. How about I walk you through this last one? Okay. Well, I'm going to get a factor of, so maybe somebody, what do I get for this factor right here? For this vertex?
Same as before, minus I lambda.
Very good. What about for this one?
Same.
Again, minus I lambda.
Right. So I get 2 factors of minus I lambda, right?
And these will be multiplied?
Exactly.
Okay.
Everything is multiplied.
So were they different contributions, like different interactions? So would they be added, or everything is always multiplied?
So the scattering amplitude to this object, so this guy is equal to the sum of all possible ways in which the particles can interact. Okay, but each individual contribution, the Feynman rules, what they tell us is how to evaluate that one term, which is itself a product of different contribution, different things. Okay. Yes, Aditya.
Is it because that we express m in terms of like exponentials, and sort of like when we multiply exponentials, we get to add whatever's in the exponent? Like, is that the reason we multiply?
Yeah, that's right. So the way that the origin where this comes from is that the way that you talk about the evolution of states is in terms of functions that are exponentials of the dynamics of the system. And so what you're doing is that you're bringing down different terms in the exponential perturbatively. That's the origin. I just didn't want to jump. I didn't want to talk about that because it's a little, but yes. And that's where the symmetry factor comes from too. You have coefficients that basically, you have coefficients from doing Taylor expansions of the exponentials. But then you also have many different terms that contribute, that have the same contribution. And it just so happened that this cancellation between the coefficients associated with Taylor expansions and the redundancy of terms can be simply evaluated by introducing a symmetry factor. Great. All right, but we're not done with this term. So let's not get distracted. So remember, the momentum going through here is P minus K. The momentum going through here is K, right? And so the momentum has to be conserved, right? So from here, it has to be P minus L, right? And therefore here, it has to be L. Such that in the middle, right, the sum of the two momenta is P, just as the same as the final, initial, as well as the final. Okay. Let me finish. Oh, go ahead.
Why do we have another factor L? Like, won't the momentum K continue?
No.
Or is this representing intermediate changes?
So the momentum, the only thing that gets conserved is the total momentum, which is
right.
P.
Okay.
And so the total momentum has to be conserved, but the individual momentum does not have to be conserved.
Got it. Thank you.
Got it. Okay. And this is the same in classical mechanics, right? If you smash two billiard balls, right, they can go off in different directions, right? They don't. The
right.
individual particles don't have to be have the same momentum as the initial ones. What does get conserved is the total form momentum, assuming the reaction is elastic. All right. So, well, there was this statement, seemingly cryptic statement, that this momentum right here, this L, is not fixed. It can take on any value. And so Feynman tells us for any momenta that is not conserved, I need to integrate over it. And it's a 4-dimensional integral. So I have to integrate over that. Okay. And then the next thing is I have to integrate, right? And I have propagators in between. And the other thing, that the first thing that we said, or this one of the first things, right, is for vertices, I get a minus I lambda. External legs I go to 1. And for internal propagators with momentum P, I get this thing. And so I need to put in the propagators for the internal ones. So I get a I over P minus L all squared plus M squared minus I epsilon. Oh, sorry, I messed up the sign. If I make any mistakes today, it's because I'm sick. So I have a good excuse today. All right. Okay, are we done? So I put in a propagator. This propagator is for this guy, right? This propagator is for this guy. Is that it? Am I done?
So I guess we need to impose the symmetries.
The symmetry factor. Very good. Okay, let's go back. So, all right, so let's look at our list. We said, for external vertices, we do this, right? Check, we did that. For external legs, we do this, great. For internal propagators, check. Intermediate momenta, you gotta integrate, check, very good. And then we gotta divide by the symmetry factor. We haven't done this, okay? And I said, it's the number of permutations of the internal lines that leave the diagrams unchanged. All right, let's figure that out. So here, the way you can think about it is that I have two internal lines, right? These two guys. And I could have, in principle, move this line over here, and then this guy over here. Basically, I can permute these two, right? I can change these two. In other words, I could have called this P minus K, P minus L, and this one L, and nothing would have changed. And so I have only one permutation. So I have, meaning I can permute between those two. So I have two contributions that leads to the same diagram, right? The first one and then the second one that I draw, right? And so I have a factor of 2 in there. I have two permutations. Okay. And that's it. That's the contribution to this thing. So, all right, Asha, you have a question?
Yes. When we multiply by these factors for the internal lines, is that within the integral or outside of it?
Oh, so you mean the propagators?
Yes.
This thing? Yeah, they have to be inside of the integral because I'm integrating over L, right? And notice this depends on L and this depends on L.
Right. Okay.
So it has to be inside of it. Yeah, Aditya?
Yeah. So how would we distinguish between like a case where two particles interact and form two particles, or two particles interact and form three particles? Because each time we sort of multiply one for all external lines, right? So it won't be different for, like, if we multiply 1 3 times or 4 times or 5 times.
Let me, I'm not sure. You're thinking about 2 to 3 transitions?
Yeah, so the second rule, I guess, mentioned that you'd have to multiply 1 for every external line, right?
Yeah.
So if we have 3 external lines, we would just multiply 1 5 times. That won't change it, right?
That's right. That's a
Oh,
trivia one. So this one, this rule right here is trivial. Like, it doesn't do anything for this theory. This is not going to be play a role in any diagram that you consider.
Oh, so it's just like to kind of construct the lines.
Yep. I mean, it's going to be, it is important in other theories. That's why, it's important to keep that in mind, this is specific to this theory. It's not in general true. All right. So I'm kind of running out of mental juice here. So Rahul, what's your question?
Oh, just one quick question and another one about the integrals itself. The first one was the order of the coupling parameter that we have in rule 1. Like when you get the final contribution, is that the same order that we talked about in lecture 1 that we tune for to find resonances?
Say that again. So that, oh, you mean, no, say that again. I'm confused.
So the coupling parameter, when
Lambda.
you multiply all the contributions, you get some kind of order, right? Is that the same order that we tune for to get resonances?
No. Okay, so maybe the question more generally is like, how does this relate to scattering amplitudes that have resonances? Is that where your question is trying to get at?
Probably, yeah.
Okay, so that's trickier. And you have to do what you essentially have to do is evaluate for resonances. You need to evaluate all possible terms. So you need to have something like basically all the possible terms that contribute. You need to figure out, you need to have a framework that allows you to evaluate all the possible diagrams. And you can do this. And we've done this using something that is called O-orders perturbation theory, but you can do it leaving some unknown function, but you can describe what those mathematical properties are of these unknown functions. Basically, for this to have a resonance pole, you need to be able, you're not going to recover it at any one order in perturbation theory, which is what we're doing. And so you need to figure out a way that you can sum all these diagrams to all orders. And Feynman diagrams can help in that, but they're not, you're not going to be able to calculate one by one, which is what Feynman rules are most useful for. So I think Andrew is going to talk about next week about different parameterizations of scattering amplitudes, and I think he can retouch on this question. He's going to talk about resonances basically. Okay. And that may be the last meeting that we have too. So that's a separate point.
That was okay. So in the integral, do we have an increment there? Like what exactly is the increment?
Oh, you mean the range of integration?
Not the range. What do you call that? Like a dx of some kind?
Yeah, it's right here, dl.
Okay, so okay, I'll just DM you on.
So this is equal to dl0, which is the zero component, dlx. This is a multivariable measure. And I'm not expecting you guys to be able to evaluate these things. So you can just use these symbolic intermediate, this symbolic representation. It's just, at this point, all I want you to get an intuition for Feynman diagrams, what they mean, and to be able to write them down yourself. I'm not expecting you to be able to evaluate these integrals. That would be something you would see much later. But I wanted to at least get the intuition that these Feynman diagrams are mathematical objects, okay?
And we wrote down, so from rule 3, we wrote I divided by p minus r squared, all of that. That's not part of the integral itself, right? That's separate.
The I epsilon?
Yes.
So the I epsilon is there to tell you how to evaluate this integral.
Okay.
So you can evaluate these integrals. A lot of times you can evaluate them analytically. So I see somebody asking if you can evaluate numerically. Sometimes you can, but a lot of times you can evaluate these integrals analytically, and the epsilon is telling you exactly how to evaluate them. Okay. Yeah, no problem. Okay, so let me leave you with some final tasks for you to do. All right. 1. Evaluate the symmetry factor for, so just the symmetry factor, not the whole Feynman diagram, okay? Just the symmetry factor for A. Here, let me do it a little simply. This is allowed, right? There's nothing telling me that this is not allowed in my theory, right? I have a vertex with 4 legs attached to it. Okay. B. Right. And remember, the symmetry factor is associated with the intermediate legs, right? Not the external ones. And then let's do one more. Trying to think about a not so complicated one. All right, this one. Okay. And then 2, write down the expression for this would be P minus K. Well, let's call this one K. P minus K. Let's call this one L. P minus L. And then A. And then B, same thing. P minus L. P minus K. So these two are exactly the same. I'm just interchanging what the momentum that the individual particles have at the end. Okay. All right. Are there any questions about that? Adriana, I think you have your, did you want to say something or?
No, I was just kind of walking through it mentally to make sure I didn't have any questions.
Sounds good. All right. If there's any questions, you can always leave them in the Slack chat. So, all right. Then, so next week might be the last meeting that we have since our semester is about to start, and I'm lecturing. So, but so Andrew's going to talk then, and then we'll continue staying in touch, and eventually I can work on partnering you guys with some other researchers, and some of you can continue working with me if you enjoy. So, but we'll talk about this later, okay? All right. I guess Aditya liked this. I'm glad. All right. Well, hope everybody's doing well, and I'll talk to you soon. Okay, we'll see each other next week. All right, take care. Oh, thanks, Christina. Yeah.
Thank you, yeah.
All right, take care, guys.